Does everybody have a consistent understanding of what's important, what the project objectives are, and what's going to create value in this context? And if they do have a consistent understanding, then that's a very good indicator that the project is more likely to succeed. So those two important things. One is listening and understanding how to listen. And the other is to have a consistent understanding of what's important. So if you're in a position where you don't understand what's really important, for goodness sake, ask.
Making sense of specialized engineering knowledge is not easy. A majority of the technical know-how is actually learned informally on the job and by doing. If you're fortunate enough, you've had an incredible mentor who's shown you the tricks of the trade. If not, don't worry about it, because this podcast will serve as your own personal tribe of mentors. In each episode, we will extract tribal knowledge from top engineering and manufacturing leaders to help you on your journey. There's really no way of knowing what information you're going to need around the next corner of your career. So let grinding gears be your guide. Hello, everyone, and welcome back. We decided to break this first episode up into two parts. Why? There's a ton of valuable and useful information, but the entire duration of this interview was about an hour and 20 minutes. We've post-produced it and cut it up as much as we possibly can without losing a lot of the wisdom that James Trevelyan shares with you. In part one, he really shared a lot of his background, his experience, and some of the wisdom that he gained, which helped him to write this book, The Making of an Expert Engineer. And more importantly, a lot of the research that went into writing the book. In part two, James talks about the things that drive commercial value for organizations, how companies can really help young engineers coming in to get up to speed with the knowledge and wisdom they need to have to become an engineer, the different types of knowledge that exists as an engineer and what you need to know to be effective in your career, and much more. So again, without further ado, we'll dive directly into the episode. Part two of this first episode. Thanks for joining us.
Kids coming out of school and anyone that's gone through engineering curriculum or curricula at a university comes out and has this understanding of the engineering type of work they want to do. Like you said, it's exciting, challenging, solving problems that haven't been solved before. That's what they're anticipating is going to be done in their profession. And then reality sets in, and that's not the case. It's really about collaboration. It's really about understanding these key factors that you're pointing out. If the engineers don't have that understanding coming out of school and then actually in the working world, what about CEOs of companies? What about the investors in these companies? Like, do they even have a firm understanding of what some of these engineers are doing?
No, they don't, for a start, but there is an incredible degree of frustration among them about engineers. And it manifests itself in different ways. For example, one CEO that I was talking to, who runs one of the largest engineering organizations in Australia, this is an organization that depends for its very existence on engineering. He says, whenever I find an engineer in my organization, I sack them on the spot. I am so frustrated with them. Now, that's an extraordinary statement for a CEO that depends on engineers every day of his life. So the question is why? Well, I think the simplest way I can describe it is that the kind of understanding of what creates value in an organization is very different for engineers than it is for the CEOs and the investors. And that's because there is no teaching about value creation in universities that train engineers. And this was another really interesting finding. Having studied what it is that engineers do, the next logical question is, why do they do what they do? And why do they not do what they push to one side? For example, engineering checking work, design checking work. And it turns out that value understanding, or how people understand what creates value, is crucial in answering these questions. So what we discovered is through asking questions like of engineers, what is it that you're doing today, and how does that contribute commercial value for your organization? Very few engineers could give us sensible answers. They would say something like this: oh, well, it's going to save 5% of our fuel costs. It's going to save 10% of the material cost on this particular part. And so engineers can readily identify value creation through, efficiency measures like that. But when it comes to issues like risk, which is what dominates the perceptions of investors, engineers think in terms of quantitative risks and trying to predict the probability. So when it comes to risk and understanding risk, engineers see risk as an exercise in quantitative prediction. What's the actual probability that something's going to fail? Whereas for an investor, risk is all about perceptions. Like, can I trust these engineers to actually do what they promised? And what's going to happen to the price of oil in the next 5 years? Something which engineers would say is intrinsically unpredictable. These are the risks which investors talk about. And it turns out that providing reassurance to investors is one of the key jobs that engineers have to do. When you look at how projects start, and they generally start with a series of feasibility studies, and then you get more detailed planning, and you get what's called front-end engineering design or FEED, and then that's followed by detailed engineering. The detailed engineering really only starts when the final investment decision has been made. And when investors do that, essentially they're putting up something like 90% of the whole project cost in the knowledge that if it goes wrong, they'll never get it back again. So they spend the first 10% on smaller studies, and it's all about building sufficient confidence to make that final investment decision. But engineers are not taught to understand how investors approach these decisions, and consequently, in that absence of any teaching about what creates value in engineering, engineers develop their own ideas. And those ideas have a lot to do with, for example, a certain degree of technical perfection, elegance, trying to find a solution which is really elegant, trying to push limits. So, for example, so many engineers have come to me with frustrating stories of how they put up a project proposal, they do the net present value calculation, it goes up for some decision, and it comes back saying, we decided not to go ahead with it. And yet the net present value calculation showed that the project would be extremely profitable. And engineers have difficulty understanding these kinds of decisions. They seem to be totally arbitrary. Well, what's entering into the decision making for the investors and the board directors is this question of risk and uncertainty. How confident can we be about the uncertainties associated with this project? So, a senior engineer told me how he had gone in to review a major mining project and found that something like $100 million had been spent on detailed design work, and the engineers had not even thought about 8 showstopper risks. These are risks which would stop the whole project in its tracks, like, for example, a hurricane hitting the main construction site during the middle of construction. How would you deal how would you avoid massive erosion damage from roadworks half completed? The engineers thought, well, these are extremely unlikely events. In any case, we're really not quite sure, how to approach them. So they had simply decided not to deal with those risks. And as a result, that $100 million had been wasted because there was no point in doing all the detailed stuff until those risks had been addressed.
And to me, James, this is another example of the skills gap in engineering and manufacturing that everybody talks about. They say that a lot of tribal knowledge is dying because baby boomers are retiring and taking that knowledge with them. Case in point, an example, this senior engineer was able to recognize, hey, look, you guys shouldn't have done these detailed drawings because you're not even thinking about some of the showstopper risks that could be associated with this project. And you went ahead and did all these detailed drawings without thinking about, hey, look, a hurricane may affect this project.
But I guess the question that I have for you is, how do people get over this skills gap? I mean, how are there systems? Are there different ways that, you've identified in your book, and more importantly, just in your research in general, because you spent a lot of time on this topic? Are there specific ways that, some of this knowledge can be acquired, obtained from, maybe some senior experts? I think it'd be pretty difficult, but, what have you learned, and what's some of the stuff that you've experienced over your career?
Well, that's a really interesting question. It's largely a matter of luck, and very few companies actually do it these days. You go back 30 or 40 years, and you would find in the US, for example, that major corporations had their own universities, where a lot of this stuff was taught not necessarily explicitly, but it was taught in a practical sense. So engineers were made to do certain projects that seemed very cumbersome, that seemed very bureaucratic. There was a lot of paperwork. And at the end of it, these engineers developed an understanding of what you had to do to get a project done without actually having ever had that written down in front of them. And of course, these corporations had very carefully constructed processes and procedures, and that's what made them into big companies. Now what we're finding is that those universities have been dismantled because companies will say, well, is there any evidence that they actually work? And they'll also say things like, well, why should we be training engineers in our universities only to see them leave and join our competitors or to join smaller companies and start up their own companies? How do we hang on to that knowledge? There's no point in teaching it to everybody. So a lot of these training departments or universities, have been closed down, and even for a lack of understanding of what it is they should teach. In Australia, for example, and in the UK, the vast majority of engineers on leaving university went to work for public service engineering enterprises like Public Works Department, railways, energy utilities, and so on. These are all government-owned organizations. And management experts came in the 1980s and said, well, these are very inefficient organizations. The private sector does it much more efficiently. You should outsource everything to the private sector. They did. And for a while, it worked really well because the private sector had drawn on the best of the engineers from the public sector. But of course, what was not outsourced to the private sector was the training that these government utilities were doing in a rather ham-fisted way, mind you. It was bureaucratic. It was mind-numbingly boring for many of my fellow graduates who went into these organizations. And so, of course, around 2000, the early 2000s, we suddenly find that engineering performance starts to drop away. And now we've reached a situation where in engineering project delivery terms, we globally have an appalling reputation. Typically, projects over $1 billion, only 1 in 3 succeed. Smaller projects, maybe 2 in 3. And by succeed, the success criterion, and this information, by the way, comes from the top US-based companies that assess project success around the world. The success criterion is that the investors get at least half of what they were promised. And what sort of a success criterion is that? Now, if you make the success criterion say something like 80%, then hardly any projects would succeed. Now, can you understand why CEOs are so frustrated with engineers? The difficulty is that they don't understand why the engineers can't produce. And lots of people earn money teaching teamwork to project organizations and so on. But because that's all based on stuff out of management schools, which does not understand, there's no understanding of the technical dimension there, it doesn't work in practice. So let me give you a really good example. So project management as a discipline originally emerged in the aerospace industry, and I was part of that in the 1970s. We were actually developing a lot of the techniques which have become standard throughout engineering industries around the world. Critical path planning, network analysis, and resource allocation, all these basic things. Now, once project management was understood as something that you could apply in lots of areas, for example, running hospitals or civil service administration, it was abstracted from its engineering context and taught as a discipline. Yeah, I'm sure most of your audience will be aware of organizations like PMI, the Project Management Institute, and so on. Now, it turns out that there's a really critical component of engineering project management which has escaped understanding, and that's how to write specifications. Because the technical specifications determine, in the end, what it is that you get in your engineering project. And so, because that's a technical discipline, it's not needed when you're doing project management, for example, in a non-technical situation like marketing or organizing public service projects and so on and so forth. Now, find me an engineering school where students are taught how to write engineering specifications.
I'd be hard pressed to try and find an example, but why isn't this being taught?
Because engineering academics say it's trivial, just paperwork, administration paperwork. But let me give you one example of where a simple mistake in a specification cost tens of millions of dollars. Somebody wanted some instrumentation down a gas well and had figured out that it needed to operate over a pretty wide temperature range. And, I'm not going to give you the actual temperatures, but they wanted to operate, they calculated, between minus 47.3 degrees and plus 75.1 degrees. And those temperature values were typed into the specification documents, not only for the company that produced the overall instrumentation system, but also for the company that produced the sensor package, and then again for the company that produced the actual sensing elements. Now, all three companies looked at this specification and said, oh my goodness me, for us to prove that this equipment is going to meet that requirement means we have to build test chambers capable of controlling temperature to 0.1 of a degree centigrade. And all three companies constructed test facilities at the cost of many millions of dollars each, simply because somebody had not bothered to say, well, okay, so that corresponds to a temperature range of, say, minus 50 degrees to plus 75 degrees, which is close enough to a military standard specification. And if they'd done that, noticed that difference, it would have saved tens of millions of dollars in constructing test facilities when there are already existing standardized test facilities that will, for example, tell you that components will work to a military standard specification. So it's simple things, simple mistakes like that. Another one, I can give you an example. In a project which I was working on myself, this was an aerospace project. We had participants from the US, Germany, Britain, and Italy. And it turned out that there was a fundamental misunderstanding between the different parties on what a specification actually was. So, for example, the British people, and I was a member of the British team at the time, the British team said, well, a specification tells you how something is supposed to work. And, if it says that the component must withstand a certain level of vibration, well, you test it to that level of vibration, and if it fails, the component is rejected. The German approach was, well, yeah, but if the component is not exactly the right color and exactly the right shape as specified, then it doesn't meet the specifications. And the British side said, well, really the shape doesn't really matter as long as it works. And the color doesn't really matter as long as the client accepts it. Now, that was okay. That was difficult enough. But when the American team came in and produced equipment which failed the British tests and certainly didn't look like what the Germans were expecting, there was a very heated meeting, a very heated discussion in a series of meetings. And what transpired was that the American interpretation, at least by the company that was involved at that time, because I haven't done extensive studies in the US, so I can't tell how universal this understanding is. But the American company understood the specification to be an aspirational goal. In other words, that the products that would come off the production line eventually would meet the specification once all the production problems had been ironed out, and that it was no surprise that the prototype wouldn't perform anywhere near the specified level of performance. And even if the early units off the production line didn't meet the specification, once they'd ironed out all the production problems, they come back and retrofit the early items so that they would perform eventually at the specified level. So you can understand here how fundamental differences in the way that specifications are understood caused immense contractual difficulties and tied up an enormous number of engineers for an awful long time, simply because everybody came with their own assumptions, because there's no clear universal understanding of how specifications are supposed to work. In fact, a specification is regarded as a very tediously long document, and you want to avoid having anything to do with it if at all possible.
One of the things that I want to talk about, because those are some really good examples, are, what are the different types of knowledge that exist? Because obviously, the technical specifications that people have to follow specific standards and say, here's the way that this product needs to be completed. But again, your example of talking about from an organizational standpoint and from like a CEO or an investor standpoint, hey, look, we want to make sure that we're taking into consideration the fact that, we're going to be constructing this product during hurricane season. So can you talk about, some of the different types of knowledge that, exist within an engineer's brain and how important it is to leverage the right ones in the right scenarios?
Yeah, I've done this in the book. So in the book, I talk about several different kinds of knowledge. First of all, what is it that we mean by knowledge? And for that, I've drawn on a definition by a Japanese fellow, Nonaka. You say, well, knowledge is true justified belief. In other words, fundamentally, it's something which we believe in our minds, but we have reasonable justification that belief is backed up by evidence. Then we say, well, what are the different kinds of knowledge? First of all, there's what we would call explicit knowledge. That is the knowledge that you study for examinations. For example, Hooke's law that stress is proportional to strain. This is knowledge which can be written, and because it can be written, it can be transferred instantly using, for example, the internet and books and so on and so forth. Straightforward. Then we come to the other kinds of knowledge which we need. There's knowledge which we call implicit knowledge, which is knowledge that's not written but could be if needed. For example, when you first started in your first job, one of the most important things to know is where's the toilet. Now, it's quite possible in some buildings there's a detailed map on the board, on the wall, and you can go to the map and consult the map and figure out where the closest toilet is. But most people turn around to the person sitting next to them and say, "Excuse me, Mary, where's the toilet, please?" And Mary will give directions, right? In other words, the location of the toilets is not something we write down. Yeah, there may be signs in the corridors, but it's that kind of thing is what we call implicit knowledge. Knowledge which could be written, but generally isn't, because it's just not convenient to write it down. Then there's another kind of knowledge called tacit knowledge. Now, tacit knowledge is knowledge that exists in your mind, but you're not aware of it. And the classic example coming from the British philosopher Michael Polanyi was how to ride a bicycle. You could probably write 10 volumes of 500 pages each on the details of how you actually ride a bicycle, but no one would ever read it. How do you learn how to ride a bike? You get on there and you fall off, and you get on again, you fall off, you get on, and eventually you manage to ride it by watching what other people do, or you figure it out for yourself. Maybe even you watch a YouTube video. The point is that you build up this knowledge inside your body. It's a combination of knowledge in your brain and your muscles and your nervous system. It's a series of coordinated movements that you do. But there's many other kinds of tacit knowledge. Go and have a look at a building site and ask yourself how much of what you can see is actually represented on the drawings. For example, there'd be probably a crane there. Who figured out where the crane would go? Who figured out the details of all the scaffolding, right? So tacit knowledge that builds up in the minds of engineers and people who actually do the work enables them to do all those things without having to have it written down on the drawings. And when you think about it, engineering drawings and documentation typically describe the end product. How you get there is not actually described on the drawings. For example, most electronic circuit diagrams leave out the power connections because you don't want all those extra lines. They just get in the way of understanding the essentials, which is how the signals can move from one device to another. And I've been in the actual position where a very skilled electronics technician has assembled a complex circuit for me and forgot to put the power connections in because they weren't specified on the drawings, right? So there is an awful lot of implicit and tacit knowledge which we build on in engineering, and we've talked a lot about it in this conversation. So the question is, how do engineers get access to it? You can't learn that stuff even if you had 10 lifetimes or 100 lifetimes. So we collaborate with other people who've got the knowledge because there's simply not enough time in the day to acquire it for ourselves. And that's the basis of this question of technical coordination. It's how you persuade people who've got knowledge that you need to get something done today that would take you a week to learn if you had to do it yourself. And it's just not practical to learn all the time. It's much smarter to get other people in to help you. But that realization is never part of the engineering studies. And I find that this particularly affects female engineers in universities. I spend a lot of time teaching in universities, and women in particular are terribly concerned that they don't know the actual stuff that they need, that they won't be able to perform on the job because they just don't know it. Whereas the guys, somewhere in the back of their brains, they just know, well, there's lots of other guys out there and they've managed to do it despite not knowing all the stuff. So there must be a way to do it. And they get in there and eventually they find out. But when you actually look at what happens, and particularly you understand these performance problems we have on major engineering projects, you realize, gee, there's a need to do things a lot smarter. We've really got to be a lot smarter about the way we do it. And so in the book, I've tried to write this down, and some people have said, God, 600 pages, that's far too much. But really, when you think about it, it's been quite a challenge to get it all into 600 pages. And I firmly believe that, in fact, I've got, reliable evidence, because the engineers that I interviewed, some of them were real expert engineers, and they were pulling in salaries 4 or 5 times as much as other engineers of similar standing. And in the end, what is it that distinguished those engineers? They had an implicit understanding of this collaboration business and how to create value for their clients. They had developed that understanding by trial and error, and more or less by accident, and many of them couldn't describe it into the terms which I've been able to describe it to you today. But the fact remains that they're there, and the book essentially captures what it is that they do differently. So that the opening is there for any engineer to study the material there, learn from it, and you'll be able to do the similar things and make yourself a lot more valuable for your clients and your employers. And in the end, you'll be able to demand more money.
So how do you earn a lot more money? Understand how to collaborate and get the information and data you need by working with your peers and working with your partners and more senior experts. Gather that information. Number 2, do things that drive commercial value. Understand what that is. And the challenge that I see is that, again, many kids coming out of school don't really understand these principles. And even some engineers that have been working for a while don't really understand how to do things that provide commercial value.
One of the questions that I have is, what can educators and companies do to better prepare students and then, their employees, for example? Like, is there any way that, educators can do a better job preparing students to go into the workforce? And then when a new hire starts at an organization, is there a better way for that organization to be able to basically provide, either a mentor that can potentially help them, show them the tricks of the trade? Or is it really just a matter of, you got to get in there, you have to ask questions, you have to understand specifically what you need to ask for help for, and specifically what you need to look for? Like, what can both organizations and educators do to better prepare these engineers?
Well, of course, in the long run, we do have to do something about engineering education. But I have found it extremely difficult, because that's been my focus, is how to improve engineering education. And I've identified some really fundamental issues common to all formal education, which make it extremely difficult to introduce these ideas into engineering curricula. So eventually we can do it, but I'm going to put that question aside and return to the issue, well, what can organizations do? Well, what I've tried to do in the book is to provide the learning materials which organizations can apply in the workplace easily. Let's look at it this way. I've explained how, for engineers, most engineers see the vast majority of what they do as non-technical administrative type work, when in actual fact, it's the crucial collaboration without which all the technical ideas are worthless. Because if you don't get effective collaboration, what gets built will not reflect those technical ideas and won't perform as you hope. So the first thing engineers have to do is to lay claim to all that apparently non-technical work and realize that, first of all, it is real engineering, and secondly, it's much more technical than it seems. And that technical knowledge is a really crucial component. The next is I think the most effective way the book can be used is as a kind of map, so that by looking at the different collaborative processes which I've outlined in the book, engineers can then understand what they're doing and see, oh yeah, this is a part of that. So I'll give you a good example. Technical problem solving, particularly problem solving that involves multidisciplinary situations. And here I'm building on some research that I became aware of only quite recently, and that's reported in the book. A fundamental issue is figuring out what the problem is to begin with. For example, you get an automotive situation and there's some problem which manifests as vibration, and the structural engineers say, look, this is an engine problem because the vibration is only there because of the engine. And the engine people say, well, engines always vibrate, but if the structure didn't resonate at the wrong frequencies, we wouldn't have a problem. And the finishing people say, well, look, it's all to do with the soundproofing materials that you put in there. And maybe we can fix the problem that way, but we've already done our best, and the soundproofing can only go so far. So what you end up with at the beginning is essentially a multi-party negotiation, because the different specialist groups are all trying to pin the blame for the problem on somebody else so that they don't have to get involved in fixing it, or they only have to do the minimal amount of work that's going to come out of their budgets to fix the problem. Multi-party negotiations are well understood in the business arena, and that kind of understanding, when brought into the technical problem-solving arena, can help engineers enormously, because once they see it as a negotiation, there are standard techniques that you can apply to get to an acceptable answer quickly, where everybody benefits. So the important thing is for people, engineers who are working in organizations, to be able to identify and say, okay, what we've got here is really a negotiation, just for example. So by understanding how negotiations work, you can then get much more effective collaboration.
A, B, C. A always B, B, C closing. Always be closing.
So that's the idea in writing the book. It's to enable people to understand and recognize the processes they're involved in, to understand that their technical knowledge is crucial, and how best to work through problems which may be, for example, solved by writing a better specification, choosing a more appropriate standard.
Earlier in this conversation, we talked about the understanding commercial value for a CEO, what a CEO understands is commercially valuable, and making sure that they're getting that return of only 50% for the investors in a good case. Let's talk about how can we bridge that gap between what an executive, a CEO will expect from the engineers and what the engineers anticipate their workload to be. How can we really bridge that gap?
Part of the issue is language. It's important for engineers to understand the kinds of language that are meaningful for investors. And you say, well, shouldn't the investors and the CEOs understand a bit more engineering language? Well, you could say that, but put yourself in the position where you're trying to build a romantic relationship with a young woman from, say, France. You've met this young woman or this young man in Paris, and you want to have a good time. Well, if you bother to learn a few words of French, it's going to make it an awful lot easier. And so the same way, engineers don't have to learn very much in terms of how investors see projects and understand projects before they can start to bridge that communication gap. So that's what I've tried to do, is to provide some concepts so that engineers can understand that risk perceptions are the really important thing, rather than the actual risks of various events happening. So for example, let's talk about standards. A problem which rears up so often. So an engineer I met told me how, he said, the only two times I've really enjoyed myself in my career were when the client forgot to ask, has this been done before? What we're talking about here is client perceptions of risk, client and investor perceptions. Clients want stuff that's been done before because they see that as a way of reducing the risks that they face. So how do we deal with this as engineers? How do we bridge this gap, particularly if you're in a position where you want to do something that's really beyond the envelope, but the clients won't let you because it hasn't been done before? So let me tell you about one of the expert engineers I talk about in my book, Charles OConnor, who built a water pipeline here in Western Australia, 400 miles from Perth, where I'm living, right out into the desert where there was a big gold mining city. And at the time, the longest water pipeline in the world was only 100 miles long and 8 inches in diameter. And he wanted to build a pipeline 32 inches in diameter, 400 miles long. And what's more, he wanted to do it at the far side of the world, away from all the industrialized centers at that time. How did he go about persuading the investors to put up what in today's terms would be billions of dollars to achieve the same thing? What he did is he divided the pipeline into about 15 sections, each of which had a pumping station and the water was pumped from one holding tank to the next. So he argued that the pipeline was well within the state of the art because the sections were considerably shorter than the longest piece of water pipeline at that time in the world. And because he was an expert on dredging harbors, he knew that harbor dredgers used pipes of up to 36 inches in diameter, and 32 inches wouldn't be a problem. And the investors accepted that. So what this teaches us is that when we're, as engineers, when we're talking to investors and CEOs, boards, and so on, we have to be conscious about their apprehensions, their concerns, and the way they perceive risks, which is fundamentally different from our perceptions. And so we have to essentially help them understand that the project is within the state of the art, even though it might be quite different to what's been done before. Another way to do that is to rely very heavily on well understood specifications. You make rigorous use of specifications, and that's reassuring for investors as well.
So, James, what's the impact that this can make? I mean, we're talking about this from a standpoint of engineers needing to understand the language and the language barrier, for lack of a better term, that they have in understanding what impact a investor, a CEO, or just a client maybe that runs a startup, what they're looking to do. Can you help me understand and help our listeners understand what impact this can not only make for the engineer, but also for the client, the investor, if an engineer can understand some of these key principles you're outlining?
I guess there's two things here. The first is language. And how do you understand what kind of language to use? You listen very carefully to the person that you want to engage in the conversation. Unfortunately, these days, there's a lot of confusion around listening, and many people assume that hearing is the same as listening. And as I've explained in one of the early chapters in the book, mastering listening skills is fundamental to understanding language.
Do you understand the words that are coming out of my mouth?
And once you understand the kind of language, the words, and the concepts that your listener is going to relate to, then it becomes much easier for you to provide explanations and, of course, reassurance in words which will be understood. And so that's the first step is listening. The second step is to understand in this business collaboration, engineers and all the other people we work with make countless, almost instinctive decisions every minute of the day. Just for example, when you're faced with 50 or 80 emails unopened in your inbox, which ones do you open first? There's no procedure that says you have to open this one and then this one and this one. You make instinctive decisions about which ones are going to be important. What drives us to make those decisions? Well, essentially, it's an understanding of how value is created. What's going to be how am I going to produce something useful so that the organization is going to value what I do? Well, it's very important to make sure that everybody has a reasonably consistent understanding of what's creating value in that particular context, so that when they make these instinctive decisions, these trade-off decisions, they're made with an appropriate understanding of what's important. And for that, the only way to do it is to build a consistent understanding about the project objectives. When you look at the reasons why these big projects fail over and over again, one of the indicators that assessors use to understand the likelihood of a project succeeding or failing is the consistency of understanding about the project objectives across the whole project team. Does everybody have a consistent understanding of what's important and what the project objectives are and what's going to create value in this context? And if they do have a consistent understanding, then that's a very good indicator that the project is more likely to succeed. So those two important things. One is listening and understanding how to listen. And the other is to have a consistent understanding of what's important. So if you're in a position where you don't understand what's really important, for goodness sake, ask. And, if you ask around and you find that everybody has a different understanding of what's important and what's really driving this project, then that's an issue that you have to bring to everyone's attention and say, look, we've got a problem here because we're all thinking that something different is important. Unless we have a consistent idea, we're going to be in trouble sooner or later.
And the conundrum that exists here, James, is actually quite fascinating. Because on one side of the equation, you have the investors and you have the CEOs that want to make sure that this investment that they made, that realistically they're only getting 50% back based on the numbers you're alluding to, they want to make sure that they're driving commercial value for their stakeholders. On the other side of the equation, you have these engineers that don't really understand how to create commercial value and aren't necessarily thinking of all the risk factors that an investor or a CEO thinks about. So, what I want to understand is what can be done? What can be done to really bridge this gap? How can engineers do a better job preparing themselves for the job they need to do and to drive commercial value? And then on the other side of the coin, the other side of the equation, how can organizations do a better job preparing their team?
Well, I think that what you've been talking about all along here is developing skills, developing collaboration skills. And that comes down to the kind of support that an organization gives for learning within the organization. So there's a good study of a civil engineering structural consultancy, which revealed that engineers who are learning in the first few years of their career typically need around about an hour a day of one-on-one guidance, instruction, mentoring, whatever you call it. And the question arises, well, how does my organization support that? Now, part of this work can be done in the context of a project for which there is a charge code. And I hope a charge code makes sense. You know, when you fill in a timesheet at the end of the day or the end of the week, you've got to figure out which time is charged to which project. Is there a charge code to cover that one-on-one instruction which young engineers require? Very few organizations which I have been involved with have a charge code for that. So what happens is that this training is done in spare time, spare in inverted commas, which means, of course, in most organizations, if there's any pressure, it simply gets pushed to one side. So one of the measures of an organization that is really interested in dealing with this issue is to say, is there a charge code for helping young engineers understand what they need to know so that they can begin to bridge this gap? Because unless the organization actually invests time in developing these skills, it's in any consistent pattern. And that's the first prerequisite. Once there is a charge code, then it's possible to have some kind of formalized curriculum.
So it sounds like it's a two-step process. One being create a charge code, and two, set aside time for continuous improvement for your engineers on your team. We're wrapping up here, James, and I wanted to ask you one kind of final question. What advice would you give to the next generation of engineers that are looking to be what you dub expert engineers? What would be their best course of action? And what would be your parting piece of guidance here as we wind down this episode?
Good question. And here I'm going to draw on the research of others. The most effective strategy for a young engineer is to find an older, more experienced person that can give them appropriate guidance. It won't necessarily be the same person all the time, but what the research showed was that the most effective measure of performance for young engineers was their ability to form a productive and helpful relationship with a more senior and more experienced person. It's all too easy for young engineers to fall into the habit of asking their peers. It's just much less challenging to go to a peer and say, hey, Mary, can you figure this out? Can you help me figure this out? Especially if you were students together in the same class, because that's what the kind of habit you develop in class. But it's not the kind of effective habit that's going to help you in your engineering career. What you need to do is find older people, more experienced, who can guide you. And quite often, all they'll do is say, look, I'm not the right person to ask, but I'll call this guy Michael Lim. He's over in the testing section, and I'll get Michael to come over and help you. So it's just introducing you to those networks, and it's those professional networks which, in the end, will govern your effectiveness as an engineer. Now, of course, not all of us as engineers are great at mathematics. It's fine. Sometimes we need to go to a math specialist. Well, When I started engineering, I was incredibly shy. I really thought my people skills were appalling. In fact, people at the time told me that my people skills were appalling. So eventually I realized that the best way to improve my skills was to find other people who were better than I was and help me develop them. And so it's just a question of reaching out to other people, because we have all been in that position, starting on a career, not having the first clue of what we're supposed to do. So in the end, it comes down to finding people that you can ask and the people who can help you.
Well, James, I want to sincerely thank you for that. And thank you to our listeners for tuning in. Part 2 of the Grinding Gears podcast, our first episode with James Trevelyan. We really hope that on your journey, you tune into Grinding Gears to gain some knowledge and wisdom from other expert engineers as they share their stories and things they've learned along the way in their career that can possibly help you. So, James, again, thank you so much for your time. Thanks for sharing a part of your journey with us, and we bid you farewell.
It's been my pleasure, Pisanio, and I really hope that some of the young people who are listening are going to get some benefit from all of this, and it's really wonderful initiative of yours to take this up and run with it.